Okay, let's unpack this. 3D printing. I mean, it's really changed the game since, what, 83 with Chuck Hull. We see it everywhere. Custom prosthetics, detailed architectural models. Amazing stuff. But anyone working with it, or even just following along, knows the big elephant in the room, the plastic, that environmental footprint.
Yeah, it's that classic trade-off, isn't it? We often just accept, okay, if I want something sustainable, maybe it's not going to be as strong, not perform as well.
Right.
But what if we didn't have to make that compromise? Especially with something as potentially transformative as 3D printing.
Exactly. And that's really what brings us to our deep dive today.
Yeah.
We're looking at this really interesting solution from MIT's CS, that's their Computer Science and Artificial Intelligence Lab. It's called SustainaPrint. And our mission really is to show you how this could potentially let us have stronger and greener 3D prints. No more choosing one or the other. So if you've looked into greener manufacturing, you know the problem. Sure, there are eco-friendly filaments out there, biodegradable stuff, recycled materials.
Right, they exist.
But they tend to have this one pretty major drawback.
The brittleness.
Exactly. They're often just too brittle under stress. So forget using them for, structural parts or anything that needs to bear a load.
Yeah, they just wouldn't hold up, which really limits their use cases, doesn't it?
Totally. It's been a real bottleneck.
And this gets engineers and designers thinking, right? How do we solve this? Is there a way to make something that's, say, mostly eco-friendly, but still has the strength exactly where you need it?
So not an all-or-nothing approach.
Precisely. SustainaPrint's idea, which is pretty ingenious, isn't about finding one magic green material. It's about cleverly combining materials using strong filament only where it's critical and weaker, greener stuff elsewhere.
Okay, strategically combine. That sounds different.
Yeah.
How does it actually know where to put the strong stuff? How does that work practically?
Right. So it uses a tool called finite element analysis, FEA.
Okay, I've heard of that. Simulation software.
Basically, yeah. It simulates how the object will behave under load and predicts exactly where the stress points are going to be, like where it's most likely to break. So instead of just printing the whole thing out of, say, strong petroleum-based plastic, SustainaPrint looks at your 3D model, runs the analysis, finds those high-stress zones.
And reinforces just those specific spots.
Exactly. Just those areas get the high-performance filament, the rest. That can be printed with the greener, maybe weaker material. The key idea is realizing how you use different materials and where can totally change the game for both strength and sustainability. It's smart placement.
Wow, okay. So the efficiency gain sounds huge. Less plastic overall, which is great for the environment, but you keep the structural integrity where it matters. That's the theory. But how did it actually perform? Did they test this?
Oh, yeah, they did. And the results were, pretty compelling. They found that even if only, say, 20% of the object was reinforced with the stronger plastic.
It's just 20%.
Yep, a modest amount. Even then, SustainaPrint could recover up to 70% of the strength compared to printing the entire thing with the high-performance plastic.
70% recovery with only 20% reinforcement. That's actually really impressive.
It is. It shows how targeted reinforcement can make a massive difference.
But you mentioned something even more surprising before we started recording, about it sometimes being better.
Yes. That was perhaps the most fascinating part, the real aha moment. In some tests, depending on the object's shape and how it was loaded, they used a sort of dome shape as an example.
Okay.
The hybrid object made with SustainaPrint actually outperformed the object printed entirely from the strong stuff.
Outperformed? How?
It seems the combination of materials led to better stress distribution. It avoided the kind of brittle failure you can sometimes get when a material is too uniformly stiff. It suggests that sometimes smart design and material placement can be even better than just using the strongest material everywhere. Optimization beats brute force.
That's kind of mind-blowing. And you mentioned this isn't just staying locked up in an MIT lab.
Right, which is great news for you, the listener, if you're into this stuff. They've actually developed a DIY testing toolkit. Lets people figure out filament strength using pretty common things like pull-up bars or just digital scales.
Making it accessible nice.
And maybe even bigger news, SustainaPrint itself is going to be released open source.
Open source, so anyone could potentially use or build on this software.
Exactly. Think about the potential not just for industry, but especially for education. It makes abstract ideas like material science, stress analysis, structural engineering really tangible and hands-on.
Yeah, I can see that. So wrapping up, what we've really explored here with SustainaPrint is this this really clever way to blend performance and sustainability.
Mm-hmm.
It kind of proves you don't always have to make that harsh trade-off. Smart engineering can find a better way.
It definitely does, and it leaves you with a bigger question, I think. As we keep pushing manufacturing and trying to be more efficient with resources, how much more potential is there in focusing on smart, localized design, rather than just relying on sheer material volume or raw strength? Maybe the future is more about designing intelligently with the materials we have. What else could that unlock?